So start streaming. Welcome back, live from my basement. I'm beginning to think that I will never make it to campus on a full Tuesday or Thursday ever. This is our fourth class in a row Zooming, but at least it's better than nothing. Hopefully everybody is safe and stays that way. Given how the interruptions that we've had in the schedule, I had to juggle the first quiz one more time. I realized that you're not going to have all the information that you need to complete it by Tuesday, so it's now going to be due a week from today. It's 4 questions. It shouldn't take very long. It is available to you. After today, we should be able to do the first 3, and then the 4th one, hopefully, we can finish on Tuesday. So I will likely be juggling the quizzes to make sure that they align with the topics that I had wanted them to as we continue to adjust the syllabus. So what is due this week, though, is homework 2 on Friday. Does anyone have questions on that I can help you with? No? We're good?
I have one question. I'm just confused with it.
Hey kids, how's it going?
Can I type in?
Anyone else have questions while we're waiting for her to come back? I've got the homework up here.
For the macro, so should we only run that macro once, then we just use the call that macro, that command? So like we don't need to every time run the whole macro.
That is correct. Yeah, you load it into memory once, and then the calls to it, the single line calls where you fill in the arguments, that's the only thing you need to run when you want to use it.
Okay. So does it matter where we put the macro? Like should it always before the models? Or?
It doesn't matter. I tend to put it up front because I put anything that the models are going to rely on before they occur. But as long as you've run that code and it's in memory, it shouldn't matter where it is.
Okay. Thank you.
Okay, so Harry has a note for us. Can you type here? Yes, you may. I wonder if you say the main effect is marginal main effect. Do you want to hear that again? Marginal versus simple versus conditional? Yes, okay. So this is just drilling, this is, I would say, what's the word I want? Prefacing a distinction that's going to become relevant later in the semester about how we talk about main effects. So in the handout that we looked at last time, and in this homework too, you have only main effects of the predictor variables. You have no interactions. And so what that means is that the slopes that you get for the effects of those predictors are constant across the sample. They do not depend on the level of any other predictor. Another way of saying that is that they are marginal main effects. They apply marginally throughout the data. The alternative is a conditional or simple main effect. Both of those terms mean the same thing, which only applies if the predictor in question is part of an interaction term. So for instance, in the example that we did last time, we had age, grip strength, and gender. If I had a age by gender interaction, then I couldn't just talk about the effect of age, the main effect of age. I would have to be more specific. I would have to say, this is the main effect of age for men, or this is the main effect of age for women. The interaction in the model implies that there is going to be some level of gender difference in the age effect. So the correct way to refer to that age effect in the presence of an interaction is as conditional, where the one that's given to you by the model is for whichever gender group is coded 0. So does that help, Harry? Okay, I've lost my window. Where did it go? There's my chat. Okay, there it is. I found it. Sorry, I'm a little slow on the uptake with technology here. I'm too old for this. But yes, okay, she's got it. Any other questions? You can type them or say them as needed.
No question. Just
no question. Okay, no worries. Thank you for joining us. Are you safe at home?
No, actually, I'm in the classroom.
You're in the classroom. I'm sorry. I have to be home because my son is here.
Oh no, no. I mean, I get the notice, but
Yeah.
since I'm in school, it's just easier to be in the classroom.
Yes, fair enough. Well, enjoy having the space to yourself. I am really hopeful at some point I'll get to see all of you again, but we'll find out, right? Well, if there's no other questions, are you guys ready for something new?
Yep.
Yep. Okay, great. Then let's dive into Lecture 3. All right, so I am hoping to get through this and exam chapter based on a handout I had already made for classes. So if you read the chapter, it will sound a whole lot like what it's going to sound like coming from my mouth right now. A good deal of in-person consistency, I would hope. So just to review the framework that I'm working from here and thinking about what goes into a model. All models have two sides. Last week, or I guess Tuesday, and last week, we focused on the first part, the model for the means. And so that's the part that's in red here on slide 2, the idea that the model has fixed effects of predictors, usually that are designed to answer some sort of research question or test some sort of hypothesis. And in these models that we're looking at so far, which are considered general linear models, which are appropriate when each person contributes only one outcome, those are called fixed effects because they're constant for the sample. They're fixed across persons. Everybody gets the same BO, everybody gets the same beta 1, the same beta 2, and so forth. Now we're switching to the other side, and we're going to focus on that for the next several weeks. And this is the idea of the model for the variance. In a general linear model, the model itself is represented just by the E at the end of this equation. More specifically, the parameter is the variance across the E's. That's what we're interested in. The E's for separate people are never part of your output. They are not estimated parameters. It's their variance that we care about. And we're going to have another type of E introduced here that's the same deal. So just to remind you of things that you may have learned at one point and may not be fresh in your mind, variance, covariance, and correlation. You are going to hear me talk a lot about covariance, and I have found it useful in the past just to remind people that they know what that means. So you know what variance is, right? How far off from the mean an observation is squared divided by sample size minus the number of fixed effects. You know what correlation is, the idea of association on a standardized metric, which ranges from -1 to +1. The middle one here, covariance, is unstandardized correlation. It's how much two variables go together in their original metric. So we only need to know two of these things to be able to figure out the third. And the models that we're going to talk about in terms of the model for the variance, the parameters of them are either going to be variances and covariances, or they will be variances and correlations. But if you know two of them, you can always get the missing one. Most of the time we're going to be talking about variance and covariance then is just the idea of association, but it's within the original metric of the variable. It makes it harder to know intuitively what the size of a covariance means. So like if I told you my covariance was 12, you'd be like, is that a lot? I don't know, because it depends on the scale of the variable. But if you know the variance and the covariance, you can figure out what the implied correlation is, which is then a measure of effect size. So are we good with this?
Yes.
Yes, great. Okay, so this is where we were last time. Empty between person model, where if you don't know anything about a person, your best guess for their outcome is the mean itself. But now let's change the story. Let's say that instead of having one occasion per person, we have 5 occasions per person. And this is like this picture, like I've taken 3 people's data out of that histogram and highlighted them. So we've got a blue person, a yellow person, and a purple person. So let's say that this is a longitudinal sample. In other words, we've got to extend our model from a general linear model to become some sort of multi-level model, which is more appropriate when we have multiple outcomes per sampling unit, such as multiple occasions per person. So in this case, if I said if we know nothing else about a person, what's our best guess for their outcome? We still start off from the same reference point. If I know nothing else, my best guess is still the grand mean. And if there's nothing else in the model, then that grand mean is the fixed intercept, the beta 0. But in longitudinal data, even before we consider the impact of predictors, we do know something else. We know from which person each observation came. So rather than guessing the overall mean as our best naive guess, it makes more sense to guess each person's mean as the starting off point. So in other words, a better guess than this red line for everybody would be the lines that characterize the mean across their observations. And the idea that we're going to start with a person's mean as our best guess is going to form later on what we'll call a random intercept. So new vocabulary term here. If fixed means everybody gets the same, random means everybody gets their own. In this case, everybody is going to get their own intercept by combining the part that's fixed plus your own deviation for how you differ from everybody else. So if we put it together, what we're saying is that the total variability in our outcome, where the empty model before would just recreate that variability in these models, for the very first model we'll estimate, the empty model, is going to be characterized as coming from two sources. First is this idea of between-person variance, which is inter-individual differences or mean differences across people. So why is it that some people have higher means than others? Well, I don't know. It has to be something about the person, something constant that operates through all of their data to give them a higher mean. So the difference between the mean lines here, that's the variability that I'm talking about. But after factoring that in, why is it that you're not always sitting at your mean? Why are some days worse than others? That we refer to as within-person variability or intra-individual differences, and this is the unique part that comes from the fact that we have longitudinal data. Okay, with me so far? Okay, so here's a picture of what I'm talking about. Let's say that I have a study of 5 occasions. These are the individual trajectories across the 5 occasions. So in this case, people don't change much, but they do vary relative to themselves, and some people are higher than the others. So in this picture, the heavy black line is meant to convey the sample mean across time, and these individual different colored lines are data for different people. So if I were to take the empty between-person model that we started with before, just a regular general linear model, a regular regression, and fit the empty model, meaning just a fixed intercept and nothing else, the e's that I would get for each of my observations would represent person. So the e for time 1 would look like this, the e for time 2 would look like this. This is the mean across time, so it's flat in this case. We've just represented the mean across all of the occasions of all the people. Here's this E number 3, 4, and 5. And that's all well and good, except that in a regression model, what are the 3 things that they tell you the E's should do? What are their 3 assumptions? Independence, normality, and constant variance. Independence is the big one here. Do you see a pattern in the E's for this purple person? They're all negative, right? This person is below the mean all the time. That's not really independent. That's more like dependent. So the E's are related. That's not supposed to happen. So what we're going to do is figure out a way to take the part of the E's that's related to each other and capture it with a different parameter. So let me introduce you to your new friend, U, as indicated here on the side. U0I is a random intercept. So it's U0 because it goes along with the idea of beta 0, meaning the intercept, but we get the I subscript because each person gets their own. Each person gets a single U0 that runs throughout their data. So in this case, what U0 is doing is saying, oh wait, purple person is below the mean all the time. I'm going to give them their own mean as the difference between the grand mean and this person's mean. So U0 takes part of what we used to call error and says it's error, but it's error that's constant to the person. So I'm going to put that over here in U0. From there, the distance between the person's mean given by this dashed line and each individual occasion is the E that's left. And now, to the best of my PowerPoint drawing ability here, the E's are independent. They're scattered around the line like you would expect. So another way of saying this is that that U0 term has captured, has predicted or accounted for the dependency that used to be there in the E's because this person was just below average all the time. So U0 is a way to build in a prediction of constant dependency, constant covariance across time, or constant correlation across time due to mean differences. So if we put that onto the picture that we had before, then we can link these ideas to the modeling terminology. So what we've done is taken the original total variation in Y, which now has a T and an I subscript here because it's per time, per individual, and we've split, we've partitioned it into two sources. One is between person mean differences. This is now going to be known as level 2 because it's between persons, and more specifically, it's this parameter right here, this U0, is random intercept. And so the variance across people in these U0 terms, that's this thing right here, tau squared sub U0. I don't know why, but every multi-level modeling book uses tau squared for these variances, and so I'm going to follow suit. In my notation, I always use a subscript for what it is the variance of. So specifically, it's the variance across people in these U0s, which accounts for then these mean differences. So you can say level 2, you can say between person, you can say inter-individual differences, and you can also add the word cross-sectional, because differences between people were there to begin with, even when you just had one occasion. So after factoring that in, then relative to where you are after each person's U0 takes you, then E is what's left over. So E variance is level 1 residual variance, and that is denoted as sigma squared. Some textbooks talk about level 1 residuals and level 2 residuals. I'm not going to do that to you. I am always going to stay consistent in my terminology. Level 1 E variance is residual variance. Level 2 U variance is random variance, and in particular, because it's U0, it's a random intercept. So when all is said and done, we still have all the variance in Y. It's not that we would talk about explained variance or variance accounted for. All we've done is take the total variance that's for unknown reasons and delineate it as for two types of distinct unknown reasons. One is level 2, which is that people differ from each other on average, meaning that's the variance that you would have had when you started at the beginning of the study. And then level 1 is the difference around each person's mean that's related to time. So if I put those ideas into a model, it looks like this. So I'm contrasting an empty means model for between person data, meaning just cross-sectional single occasion data, versus longitudinal multiple occasion data on the bottom. So note what's the same. Beta 0, beta 0. Beta 0 is my fixed intercept. It's the part that everybody gets to start the prediction of their outcome. From there, what used to be individual E has been partitioned into the part that's still individual, which is U0, and then E, which is then how far off you are from the mean. So these U's are always phrased as deviations, just like the E's are. So the mean of the E's is supposed to be 0, the mean of the U's is 0 too. So if I'm somebody who's doing better on average, my U0 is positive. If I'm somebody who's doing worse than the rest of the sample on average, my U0 is negative. Then from there, relative to my own rest of my data, if today is better than yesterday, my E is positive. If today is worse, my E is negative. And note the subscripts. We go from YI for one occasion data to YTI for multiple occasion data. And because we have multiple outcomes, we have multiple residuals. So 1 U per person, as many E's per person as they have occasions. Okay, how are we doing so far?
I got one question.
Yes.
So for the individual residual variance, here we assume that they're the same, like across all the persons in the sample, right?
Yes, we do. That is an assumption, and that's something that we can change if it's not plausible. But that's the jumping off point.
Oh, okay. So here we assume that they're the same, but we can relax that assumption.
Yes, the vast majority of cases that you see will make that assumption. So there's going to be only one parameter for E variance at level 1 and one parameter for U0 variance at level 2.
So if we run the model and we assume that they are all equal across person, but eventually when we get the estimates, we find out that they're not plausibly like equal. How are we going to like change the model?
How we will change the model is go ahead.
I mean that I'm wondering if that indicates that we are missing some covariance or like something else. I'm not sure.
Yes, well, so at this point, this model is like the worst model you could ever have, right? There's nothing in it. It's the jumping off point for adding stuff. So the assumptions about the residuals that you're making, which in this case apply to each level U and each level E are all supposed to be normal, independent, and have constant variance unless specified otherwise. What's going to end up happening is that we will introduce predictors, both fixed effects and random effects, that in turn allow the variance to differ across people and across time. If once we've done all of that, we do residual inspection and it looks like some people have more variability within persons than others, then there are other extensions to the model that you can add to build that in. Those types of multi-level models are what's known as location scale models. Have you heard of those? Nope. Okay, so it's location dash scale, like it's like a hyphen. And what they do is build in predictors of heterogeneity of variance. That is a topic that I usually cover in my advanced class, but I can give you some readings if you're interested in that. The idea that goes along with it, like let's say that we're studying something like negative affect, grumpiness as a trait, and you ask somebody every day for a week, how grumpy are you? Some people are kind of the same every day, nothing really rattles them. They're more pretty even keel. And some people are really volatile, right? We call them drama queens or drama kings, right? People like that get really riled up, and so they're just constantly like reeling from one thing or another. So if you think about differences between people, not just in how grumpy they are on average, the average grumpiness, that would be taken care of by U0. The extra thing that you're asking me about now would be differences in moodiness as a trait, differences in how much people fluctuate in their mood. And these models do assume that people fluctuate to the same extent, unless you add things to the model that allow people to differ in how much they fluctuate. Those are heterogeneous variance models or location scale models. I have some treatment of that at the end of chapters 7 and 8 in my book as well. Yes. Okay, other questions? Okay. So the first thing then that we will want to know once we fit this model is to calculate an effect size that describes the relative proportion of each kind of variance. How much of what of my longitudinal study is actually cross-sectional relative to longitudinal? So there's a very, very common and useful descriptive statistic, intraclass correlation. I'm guessing that you've seen this in other contexts before?
Yes.
Yes, yeah, it's the same idea. It's abbreviated ICC, not to be confused with item characteristic curve in IRT, which is also ICC. This IC is a ratio of variances, and I've written it out here 3 complementary ways. The bottom is total, so how much is between persons and within persons, or due to the random intercept versus the residual variance, or more specifically using the notation, the variance of the random intercepts plus the residual variance, so level 2 plus level 1. The numerator is level 2. How much is between persons due to intercept variation or mean differences specifically, as denoted by this variance tau squared here. If you picture the full matrix of the data, so let's say that I have 3 occasions. The variability across those 3 occasions would be summarized by a matrix. So on this matrix, this is a term that you're going to see in your output called an R matrix. I'm not really sure what R stands for. It could be a number of things. So we'll just, what this model is saying, this idea that we have U plus E as the model for the variance. On the diagonal, it's saying the total variability at each occasion is part level 1 due to E, part level 2 due to U. And that is the same across occasions. It is also saying that the only reason that occasions from the same person were related is because that person has a different mean, and that's it. So the only term that predicts a covariance is this U variance, this intercept variance here. And if we go back to a few slides ago and look at the formula for correlation, it's this idea of covariance over variance, and that special correlation over time is the ICC. So if I take this entire variance covariance matrix, this would be known as like sigma or something in SEM terms, and I convert it to correlation matrix, the correlations you get is the ICC. This model assumes the same correlation across all occasions, no matter how far apart they are. So the ratio then, the intraclass correlation, varies in this particular model from 0 to 1. It can't be negative because variances can't be negative. There are other types of ways to build in negative correlations across time that do not relate to variances. But in this case, it's 0 to 1. The closer it is to 1, the more of your data, your outcome, is because of level 2, is because of between-person mean differences, is because of cross-sectional differences that were already there. The closer it is to 0, the more of your data is actually longitudinal, is within persons, is intra-individual variability, is in the E's, is variation over time. So this is an effect size. I will also teach you how to do a significance test for whether or not that numerator, the intercept variability, is significantly greater than 0. Okay. With me so far?
Yes.
Okay. Are there any questions in the chat window I should be aware of? We good? Okay. All right, cool. So then, after we get to this initial model here, this U plus E variance model, we add predictors. And from there, it looks a lot like regression in the sense of what we do with the fixed effects. The only difference is in what kind of variance each type of fixed effect can account for. So U0 is between-person variance. The only kind of predictor that can account for it is a between-person predictor, as level 2 is something that's time invariant. And after we put those predictors in the model, U0 should have its variability reduced. And so we can calculate an R-square for how much of the intercept variance specifically we would have accounted for. Likewise, E is within-person variation over time. The only kind of predictor that could account for that is time-varying predictors. And we can then have e-variability left over after considering those predictors as well. So at a minimum in these models, we will have two different kinds of R-squares to consider. One for the between-person intercepts and one for the within-person residuals. One for level 2, one for level 1. So let me show you the implications for testing fixed effects of these differences of these two different models. So this is data from the beginning of Chapter 3. It's fake data, of course, so that it behaves very well. I have 50 kids who were randomly assigned to a control or a treatment group. They were each measured twice. And the idea is that my treatment should be more effective at helping them grow. So while I expect both groups to grow, I expect more growth in the treatment group. And I have here the cell means and the marginal means for each condition of the experiment. So this is the type of table that you would see in a results section, a type of table that would be used to describe an analysis of variance. And the parameters that we're going to see on our output are highlighted in red. So I'm going to set up my predictors so that the reference point is pretest and control. So that's why the fixed intercept is going to be here. And the rest of the numbers we will be able to get to as linear combinations of the model parameters as well. Okay, so before I jump in here, does this U plus E thing sound familiar to any of you? Has anyone talked about this in your classes before? If the answer is no, then that's fine, because then I get to be the first.
No.
Nope. Well, here's what this is. This is the difference between a between groups and a within groups ANOVA, or repeated measures ANOVA as it is known more generally. The way that repeated measures ANOVA was initially taught to me is that it controls for constant differences, right? And it kicks those differences out of the error term so that the tests of your repeated measures are made more powerful. Well, I never thought about the thing that was kicked out. I just accepted that it was. The thing that was kicked out of the error term, that's the U0 variance. It hasn't been kicked out of the model, but it has been kicked out of the test for predictors for which it's not relevant. And so we'll see that happen in the example that I have. So let's look at that. I have example 3A here for you. Does everybody have this ready to go? Okay. So again, we only have two variables, time and group. Here is an example of how you would take a file that used to be wide or multivariate, where it's one row per person, and we would stack it into a longitudinal or one row per occasion per person stacked type of file. So we have time, we have the outcome, and I am going to center time such that I'm calling time 1, meaning my reference is the first occasion, which is pretest. And then I'm creating a predictor called treat, which is the difference between control and treatment. So if treat is 1, that's the effect of being treated. So you can see in the labels the coding here. And here are the means I got from proc means, using class to denote that I want means per level of group and time, both aggregately, marginally each way, and then for each combination of the two. So that's where the numbers that I used to build this table came from. So let's contrast. I want to show you 4 models here. 2 that are empty and differ in their model for the variance, and then another 2 that have the predictors of interest that differ in their model for the variance. So we're going to look at proc mixed code that has a few new things on it here. So I'm on top of page 2. This is equation 3.1 from the book. So this is an empty means between person model. And I say between person because the only kind of variability that is built into this model is between. It's the analog to, let me go back and find it, this picture right here, where we're saying that all the variance is the difference between that observation and the grand mean. All the variance in one pile, as it were. So we have a few new things here. The nesting variables that denote which rows go with which people, those are always going to go on the class statement here. So I have person ID that keeps track of who's who, and I also have time, which keeps track of which occasion is which. So this helps tell the program how the data are organized in terms of which rows go with which rows for modeling purposes. I have my learning outcome here. I have no predictors because this is an empty model. And I have a new piece of syntax that you haven't seen before. This is a repeated statement that tells SAS what kind of variance covariance matrix you want for the two occasions from which each person. So it is the structure of, let me find that again, the structure of this right here, this R matrix. So the repeated factor is time. So this is being treated as a categorical nesting identification type of variable, and that's why whatever goes here on repeated, stop it, word, goes here on class. These options after the slash ask for pieces of output. When I ask for R and R core, I'm asking it to generate what the model is predicting for the variance and covariance across occasions, both in its original covariance form as well as in the correlation form. Subject equals person ID tells it how the occasions are organized that go to the same person. And then last but not least is this type. So all of the models that we're going to look at today are going to have the same type of structure in the code, but it's the type that's going to switch here. VC stands for variance components. It is an independence model. What it actually is going to look like in terms of the prediction is right here. So each person has two occasions. It is telling me, VC structure says, okay, what you've just asked for is a model in which the same variability is estimated for occasion 1 as for occasion 2, with no covariance whatsoever. So no relationship between the E's across occasions or across people. An independence model. This is a general linear model. So I call it a between-person model because that's the kind of data it would be appropriate for. The correlation version of this matrix, then, it just has the ones for the variances in standardized metric and a blank space, which means 0. And who was it earlier that was asking me about the differences in variance across people?
Me.
Okay, so do you see this right here for person ID 1?
Yes.
So SAS prints this predicted matrix by default for the first case in the data set. There's nothing that we've told it to do that would make these numbers different for person 2 or person 3, but it potentially could be later on when the model gets more complicated. And so if you wanted to get a predicted matrix for a different person, you would add like R equals 2, for instance, and it would print it for the second person instead.
Okay.
So if a person has a different combination of predictor variables, then their R matrix could be different according to the model that you've specified. But right now, you can just ignore the fact that it says for person 1 because it's for person everybody.
Okay.
So the only parameter that's in the model for the variance right now is this right here. And it refers to the variable that you use to define the repeated measures, which is time. But really, this just means residual. So here's the 40. So this is the variability at each occasion across persons. Then the only other thing that's of interest here, so blue is the model for the variance, red is the model for the means. This is my fixed intercept. Because I have no predictors, my fixed intercept is the grand mean across everybody and every occasion, and it has an estimate of 53 with a standard error of about 0.6. Okay. So now let's contrast that with our new model. So this is what I call a within-person empty means model. This is the one that adds U0. So the equation is up there, equation 3.2. Can you see the difference in the code that has allowed this model to be different? You'll have to look carefully. There's only one tiny difference.
The type.
The type, yes, right here. Type is CS. Would anyone like to guess what that stands for?
Compound symmetry.
Very good. Yes, compound symmetry. That is a lovely stats term. Just rolls right off the tongue, doesn't it? But what that means, what that translates to in terms of what you've just told the model to build in it, is an R matrix that has two things contributing to it. So note the total variance is still about 40. That hasn't changed. But what has changed is how we are saying that was compiled. Now we're saying the total variance at each occasion is 40 because it's partly within person E variation and partly between person U0 variation. Therefore, by separating the variance into these two kinds, we have made a way for there to be covariance over time. More specifically, the U0 variance is the covariance. We're saying the only reason that pretest and posttest would be related is because some people are just higher all the time, and that's it. There's only one reason for the correlation between occasions, and it's this. So the covariance that's given on these off diagonals is the random intercept variance, which is the 12 here. And if you convert that to a correlation, it works out to be 0.3. And that is our intraclass correlation. So putting it all together, here in blue are the two parameters that have been estimated by the model. Something called CS, which is the random intercept variance. That's my 12. So that's level 2 between persons, mean differences variance. The rest of it is residual, which is level 1, E variance, within persons across time. So 12 plus 28 equals 40. So we have an intraclass correlation of 0.3. You can think of that 0.3 in two different ways. Both of them are correct. One is that 30% of my total variation in this data set is because of person mean differences over time. 30% is because of level 2 random intercept variance. The other way that you can think about it is that 0.3 is the expected correlation between pretest and posttest. So either one of those is correct. One may be more useful to you to think about than the other. So if we come down here to the intercept is still 53. That's because we didn't change the model for the means yet. The model for the means still just has a grand mean in it. And if you have balanced data like we have here, where everybody has the same number of occasions, the mean will be the same before and after the random intercept. We will revisit this idea of model comparison that the rest of the boxes focuses on in just a little bit, but I want to go ahead and keep going if that's all right for now. So let's put some predictors in. So I'm going to contrast what happens to the test of the predictors if we have only an E in the model for the variance versus if we have the correct model, which is U plus E. So just to, I guess very briefly say, there is another result given here. That is the test of whether this 0.3 is greater than 0. The fact that it's significant means that it is. So this 30% of the variance that's due to level 2 between person mean differences is not ignorable. Therefore, the U model is the better model. So keep that in mind as we compare what's going to happen when we add predictors. So here's the model that would test my hypothesis. My hypothesis is an interaction between group and time. I expect that one group improves more over time than the other. So note it looks like a traditional regression, right? We've got beta 1 is for time, beta 2 is for group, beta 3 is for the interaction. Note the subscripts. Time gets a TI because it's per occasion per person. Group gets an I because it's only per person. So each person in theory could have their own set of time observations. They happen to be the same in this simple case, but that's not usually the case in real data. So then when it comes down to adding these terms to the model as fixed effects, they go here. So I want to point out a couple of things. This is an explicit way to list that I want the main effect of time, the main effect of treatment, and a time by treatment interaction. The asterisk can be used to create interaction variables on the fly. You don't have to compute them yourself as actual observed variables. So this is super handy. The other thing that's different is note that the code now features two different versions of the time variable. I've got time and I've got time 1. They are being treated differently in the model and in the syntax. Time 1 was the variable that I created at the beginning that is coded 0 for pretest and 1 for posttest. I am treating that as a continuous predictor. Since it's binary, it doesn't matter if I call it continuous or a grouping variable. But the fact that it is not mentioned on class means that it's continuous. So when SAS sees model outcome equals time 1, it's going to make me a slope for the difference between pretest and posttest. Likewise, it's going to make me a slope for this treatment variable in which 0 is control and 1 is treatment, and it's going to make another slope for the interaction of the two. Time, meanwhile, still remains on the repeated line and still remains on the class statement. That's because time is like an ID variable. It's not in the model. It's used to tell SAS which rows go with which rows in building the predicted variance and covariance matrix across time. Technically speaking, you don't have to have time here if you don't want to include it. When it matters is when you have missing data. So it identifies which row is which, so if you have a variance structure in which the expected variance or covariance changes after time, you have to make sure you tell it which occasion is which so that it puts the rows into the right parts of the matrix in terms of estimating everything. Okay. So then after this, I have added some output to request some additional information. One is the model predicted mean for each of my cells. And so that comes from the model up above. So when I say intercept 1, I'm saying the predicted mean for the control group at pretest starts with beta 0. That's what intercept 1 means. Time gets a 0 because it's pretest. Treat gets a 0 because it's control. And 0 times 0 is 0. Likewise, control at posttest. Still need a beta 0. Now I pick up a 1 because it's posttest. But because it's for control, treat is 0 and the interaction is 0. And so on down to the last possibility where only the interaction turns 1 if it's treatment group at posttest. These are simple slopes for each of the possible main effects that I would be interested in. Because these are it's a 2x2 design, you can think of these as all possible pairwise differences. So we have, or not all possible, but all the ones that would make sense to ask for, let's put it that way. So this is something that Chapter 2 talked about and that we didn't have a chance to go over yet, but I'll let you read about that. The idea that how the time effect gets predicted starts with beta 1 for time, and then how group changes the time effect. So in this case, we're talking about the time effect is beta 1 plus 0 beta 3s, meaning the simple effective time right here is for the control group. To get to what the time effect would be for treatment, we need 1 beta 1 plus 1 beta 3 because group equals 1 there. To go the other way to talk about what the group difference is, we need 1 beta 2, and now time is the moderator here, so we need to fill in the value of time for which we want the effective group. And so in this case, it's beta 2 plus 0, and then the last one here would be beta 2 plus beta 3 because it's a post-test. So of the possible simple effects of time and treatment, the model itself only gives us 2. These extra lines here that are linear combinations of betas give us the missing ones. So now, after we put in these 3 new fixed effects, we've reduced the overall variability from 40 down to 27. So this is the model where all the variability is in one pile. It's all E right now. And here is the result in terms of our fixed effects on the top of the page 5. So these numbers then match. Here's the 49 for the fixed intercept. The UR here sign is for the pretested control. The numbers on the output are in the red boxes here. So these effects of time and treatment are not marginal main effects. They are conditional main effects or simple main effects. The time effect is specifically for the control group. The treatment effect is specifically for the pretest occasion. And the interaction then gives us either how the time effect differs between groups or how the treatment effect differs over time. But note the p-values here. Wah, wah. A p-value of 0.3 for my primary hypothesis. No good. So this model would tell me that nope, my experiment didn't work. My treatment group did not improve significantly more than my control group. Bummer. So then here are all the estimates for the simple effects. So here is the time effect for each group and the group effect for each occasion. So let's see then what happens when we fit the right model. So the only thing that we've changed is adding this U right here. That means that we are separating the total variability into saying that some of it is because of constant mean differences and some of it is differences over time. So that addition of this U0 here, or really its variance as a new model parameter, shows up right here, type equals CS. So we're switching from a variance components type, which is what it was before, which means equal variance across occasions with no covariance whatsoever, and we're switching that to become CS, which means equal variance across occasions, but now we do have a covariance because the covariance arises because of mean differences, arises because of random intercept differences. So the total variability at each occasion, the 27 that we had before here, that's still what's on the diagonals. The total variability each occasion is still 27. But how we arrived at that 27 is different. We said that 22 of it was because of between-person mean differences that remain after controlling for group, whereas 27 minus 22, so here's the residual for that math there, 4.4 of it is because of remaining differences after controlling for time and group by time. So if we take this total 27 and we look at how much of that is because people just differ from each other and we don't know why, that's 84% of it. That's a big difference then in terms of saying there's no relationship over time, which is what the E-only model says, versus there's a relationship that's 0.84 in correlation between the two occasions. So these ICCs can change quite radically after you introduce predictors. Typically, we only report them from the empty model because we want to know of the total variability that is to be predicted, how much of it is between persons versus within persons. But you may also see these conditional ICCs reported in other instances. I tend not to, but that may be something that you see. Okay. With me so far?
Mhm.
Okay. Do we have any questions? See if I find my little chat window or anything. We're doing okay?
I got one question.
Please.
So, in the between person conditional model in 3.7, so we actually assume that all the observations are independent.
Correct.
From each other, right? So it's like just like a regular regression model.
Absolutely.
And for the 3.7 within person conditional model, we assume there are correlations within person because it's a repeated measure, and I'm confused because when we look at the point estimates, like for the fixed effects, it looks like, because in the between person model, actually it has more degree of freedom than the within person. It has more information than the within person condition model. Is that correct? Because we assume that we have actually more people than the within person conditional model.
The model understands that we only have 50 people. So if you look at the degrees of freedom for all of these estimates here, it is the 48. The question is, what does the model assume is the reason for the variability? And in this case, the model assumes there's only one reason. It's all variability due to one kind. And therefore, in thinking about building these tests of these fixed effects, all of that variability must be relevant because there's only one kind.
Okay.
So the formula for standard error, the numerator of it is residual variance. At this point, in the between person conditional model, it's 27. All of it. It is true that this between person model estimates one fewer parameter in terms of not estimating the random intercept variance, but otherwise it doesn't have more information. It's just ignoring what happens to be a huge dependency between the residuals from the same person.
Okay.
So I'm glad you pointed out the fixed effects because that's where I was going to go next. So here, let me see if I can get them all on the same page. Okay, I'm going to split my screen. All right, so the top is the results from the between person conditional model. And the bottom is going to be my new and improved within person conditional model. All right, can you see these two side by side here? So let me give you some easy questions. First off, what do you think about the fixed effect estimates? Same or different? Same. Does that surprise you? Or I should ask, why are they the same? Does anyone know? Because the model for the means is the same. What fixed effects are in the model are exactly the same. The model for the means is the same. It's beta 0, 1, 2, 3. So the estimates are the same. Degrees of freedom are also the same in this case because our repeated measures condition is only 2. We would have more degrees of freedom for the repeated measures if it was more than 2. But we can ignore the degrees of freedom because the interesting thing here that I wanted to point out is what happens to my standard errors? Intercept, same or different?
Same.
Same. Time effect?
Smaller.
Yeah, smaller. Treatment effect, same or different? Same. And interaction?
Smaller.
Yeah. And so because the estimates are the same, and for the standard errors that went smaller, their t-values got bigger, and now the p-values change. And lo and behold, the interaction p-value is actually significant. So let's think about why these things changed and why only some of them changed. If you think about error variability, right, unexplained variability, really, in this data set, there are two kinds. Some people walked into my study just doing better than others. I had nothing to do with that. I made sure that those individual differences were not confounded with group through random assignment. But some people are just better than others. That's just how it goes. So in terms of testing variability and testing predictors that differ between persons, like treatment, that is tested the same because all of the variability in the data is relevant in testing that. Both the variability between persons and the error term, the residual. The residual goes into everything. In contrast, if I look at the main effect of time, so if I can get them in there, no, it can't highlight them both. And the same thing happened to the interaction term. The effect of time is why is post-test different than pre-test? So when I think about reasons for error around that, the fact that some people walked in higher than others has nothing to do with why pre-test is different than post-test. It's irrelevant. There is no way that whatever I did to them over time was going to change the fact that some people are just better than others. In other words, that random intercept level 2 between person variability is irrelevant in testing the effect of time. So we're going to kick it out of the numerator of the standard error. So this standard error, the error that it's tested with is E-variance specifically, which was 4.4, not 27. And that's why the standard error is so different. Likewise, time by treatment is this idea that the groups change differently. That is a within-person effect, because it's saying, why do some people need different time effects? And the fact that some people walked in the door higher than others is not relevant in testing why some people change differently than others. The change happened within persons. So the same 0.44 error term was used to make this. So the 27 then only gets used in testing treatment because that's the only thing here that's between persons. Time and time by treatment are both within person longitudinal effects that should be tested only against residual error. And so that's why you end up with different t-values and p-values and inferences. So in this case, fitting the correct model actually gave us more favorable results because it gave us a fairer test for the within-person effects. It used only the within-person residual variability in assessing those. Does that make sense, or do you have questions? Silence. Any chat window questions? I can't get my chat window back. I don't know where it went.
No.
Nope, we're good? Okay, so this is all in the book too, so if there's any of that I said too quickly, you can check it out. But I do want to ask you this one last question here. So here's my final equation. Here's the model that I fit and decided was the best one. The how you can decide whether or not you need the U relative to the E is something called a likelihood ratio test. We'll talk more about those next time. but it's a significance test that allows you to say whether or not the U variance is significant. In this case, it is. So this is the better model. But my question is this as complicated of a model as I could have estimated? So another way of thinking about this type of longitudinal design is, instead of it being a 2x2 of time by group, I could actually think of it as a 3-way design where I'm crossing person by time by group, because each person has 2 observations. So if I think of it as a 3-way factorial design, that implies that there are 3 potential main effects, 3 potential 2-way interactions, and 1 potential 3-way interaction. So I want to ask you about what could be here relative to what is here. So first off, let's do the main effects. Do we have a main effect of time? Not a trick question, I swear. Do we have a main effect of time? I'm staring at one. Beta 1, right? Likewise, do we have a main effect of group?
We
Yes.
have single.
Yeah, beta 2, right? You're like, is she going for some? No, I swear I'm not trying to trick you. Now here, do we have a main effect of person? This is the tricky question. What if I told you, yes, we do? Where is it?
Do you mean the random intercept variance?
Yes. U0 is my main effect of person. It's a random effect instead of a fixed effect. So the difference is inference here. When I say I have a main effect of time, that means the model is trying to figure out specifically for pretest and specifically for post-test what's going on. It's not trying to generalize to any other occasions. Likewise, my effective group, specifically for this control, specifically for this treatment, can't say anything else about any other kind of treatment. U0 is a random effect. It's the idea that people differ from each other without estimating specific fixed effects for person 1 versus person 2 versus person 3. I could have done it that way. That's what's known as a fixed effects model, and that's much more common in econometrics, where you would put in a dummy code for person, and you would have, in this case, if you have 50 people, you'd have 49 dummy codes for all possible differences between persons. That would be a fixed main effect of person as a categorical predictor. This U0 is a random main effect of person. What it does is add a variance to the model across people without the intention of making inferences to specific individuals. But it is a main effect of persons. So let's do the interaction terms. So there's 3 potential interaction terms. How about time by group? Do I have that one?
Yes.
Yep. How about person by group? And in this case, each person is either in control or treatment. So could I possibly have person by group?
No.
Nope. Can't observe it in this case. So if I can't have person by group, then I also can't have the 3-way interaction of time by person by group. So that leaves only one more 2-way interaction, which is person by time. Do I have it or not?
I would say no.
You would say no? That's a reasonable guess. What if I told you I did? What's left, folks? Which term have we not talked about yet?
Residual variance.
Yeah, E. Guess what? E is person by time. It's why do people change differently after controlling for group? That's what E is. That's the only kind of variability that's left. So I make this point because I want to illustrate this problem with two occasion data. We have no way of differentiating what is a person by time interaction, meaning people change differently within groups, from what is residual unexplained error. They're bundled into this E term. So I made a picture to try and get at that idea. On slide 16 here, we look at the picture and then we'll be done for today. You can think about that E in one of two ways here. In two occasion data, let's say that these are predictions from people from the same group. On the left-hand side is the model that we have here. We have a time slope that is predicted for this group. We have each person getting their own random intercept, so their own deviation between the average for the sample and their own average. And then from there, each person gets an E for the deviation between where the model predicts they should be, including their mean, and where they actually are. So E is error. Contrast that with the picture on the right, where instead I drew different slopes for each person. Now there's no E. Because when you have 2 points, or 2 points, you only need one line. So either you believe that everybody changes the same, and you have some remaining variability for whatever reason over time, or you believe that everybody changes differently, and you've perfectly captured that change. Six of one, half dozen of the other. With two occasion data, you cannot differentiate residual error, unexplained variability over time, from individual differences in change. So E is person by time. As an aside, have you heard of structural equation models that fit latent difference scores?
No.
No? Okay, good. It's some bullshit. It's basically the picture on the right, where they shut off E in order to be able to estimate individual differences in change. But it's the same. It's just a trick. So this is why two occasion data are problematic, because we're not able to measure individual differences in change, and therefore we're not able to predict it. All we can do is try to reduce E variance. If we gave each person a third dot, then the lines wouldn't fit perfectly, and we'd be able to differentiate what is variability in the residual because of individual differences change from just within person remaining variation over time. So that's why we want more than two occasions from it in longitudinal data. So questions as we wrap up here. Okay, then we'll call it a day. We'll have assignment 2 due tomorrow by 11:59 p.m. Please shoot me an email if you have any questions, as I'm not sure if I'll be on campus tomorrow either, given that we're supposed to have frigid wind chills. And I will hopefully see you next Tuesday to be able to finish this lecture and example 3B. So anything else before we adjourn? Nope.
No, I'm good.
All right, then stay safe, stay warm, and I will hope to see you next week.
I got one question.
Please.
It's still about the between person conditional model.
Mhm.
I thought, well, initially I thought it's like, because I didn't pay attention to the degree of freedom. I thought it's just like a regular linear regression,
Mhm.
but looks like, because if it's if we run if we run this model using proc REG, I think the observation it used will be 100.
Yes.
And in that case, the degree of freedom should be like 98 or 99.
Yes. In that case,
But
and it's
here,
and it's because of this repeated here that it isn't that way.
Okay, so here is still the SAS still knows that it's repeated measure. It just assume that there's no relationship between those two measures.
That is correct. So if I took that same repeated statement that has type equals VC, and I took out the word time, then SAS wouldn't understand that I have repeated measures, and it would just estimate the same model as proc reg. The default in proc mixed, if you don't mention anything, is the same as proc reg. You get your e-variance that's independent across observations no matter what, even if you don't write repeated. So by adding in the time, I got it to understand that I only had 50 people, and to use the right degrees of freedom for that reason. And the reason that I wanted to do that is because then when we contrasted the standard errors and the t-values, I wanted the only thing to be different between models was literally the model for the variance, and thus what the numerator of that standard error becomes.
Okay, I got it.
Yes.
Okay, thank you very much.
Yes, but you are right. If I said I'm not gonna run my longitudinal model in longitudinal, I'm gonna just run it in regression and call it good, my degrees of freedom would be wrong, in addition to my variance model.
Okay. So in this between person conditional model, is it more powerful than the regular the proc reg?
It depends on how you look at it. So with this between person conditional model would have more accurate degrees of freedom for the between person effects, but it isn't more powerful because it's based on the same variance model.
Okay.
So it's the same model, it's just different degrees of freedom for the t-values. And so once you get degrees of freedom of 48 versus 100, that's not going to change things very much in terms of the significance of your t.
Okay, gotcha.
But
Thank you very much.
Yeah, I was just going to say the difference in power comes in contrasting the between person model from the within person, getting rid of the between person variance that's irrelevant, the random intercept variance, and testing the time effects. That gives you a more powerful test, but it's a legit more power. Okay,
that's
good.
Basically what I have for the questions.
Okay, can I ask you a question?
Sure.
How do you say your name?
Oh, Tianpeng.
Tianpeng.
Yes.
Okay, because I keep staring at it and knowing that it doesn't look like exactly what it sounds, and I wanted to make sure I'm getting it right. So Tianpeng.
Yes, you are getting it right.
Okay, I'm going to keep working on it. Thank you for helping me.
Thank you.
Okay, I will catch you later then.
Hi, Dr. Hoffman.
Hello.
Yeah, I have one tiny question. In the SAS, that proc mix, what does that IC stands for?
I see. Oh, it stands for information criteria. It prints the piece of output. It's called information criteria table. It has the -2 log likelihood and all the AIC and BIC versions.
Okay, got it.
Yep, that just asks you to print that extra table.
Got it.
The reason that I do that, by the way, is that it prints the parameters, whereas that's not part of the other table. Although when we're using residual maximum likelihood, those parameters are only the model for the variance parameters. They don't include the fixed effects.
Okay. Got it. Thank you so much.
Yes. And how do you say your name?
Mingqing.
Mingqing.
Yeah.
Okay. All right. Thank you. I'm going to keep working on that too.
Thank you. Have a good day.
You too.